In Europe, and much of the world in fact during the 16th century, science and religion were almost indistinguishable. The people of Europe still widely believed that the Earth was not just the center of our solar system, but the center of the universe. And while others have been cited throughout history disagreeing with this notion, it was not until Copernicus that a proper revolution of our place in the universe truly began. Copernicus's heliocentric model of the universe was not well received in his time, but later, Galileo and Johann Kepler began to champion his model, which can be summarized by the belief that 1. The planetary orbit is a circle with epicycles. 2. The planet is approximately at the center of the orbit. And 3. The speed of the planet in the main orbit is constant. And with this, the Copernican Revolution began. However, his model was not without its flaws. Thanks to Kepler, we now know that planetary orbits are ellipses, with the Sun at one of two foci, and the speed of the planet changes with the changing radius. My name is Eric Hilsberg, and welcome to Astronautics 201, where I'll take you on a journey through the space side of aerospace engineering, covering topics in orbital mechanics, propulsion, and some special topics. In this video, I'll cover Kepler's three laws, which form the basis of modern orbital mechanics, and how they're used today in the early stages of space mission design. My goal is not to cover every detail of the math and physics involved, but to provide an approachable series that builds up intuition and understanding that will serve as a good foundation. Now, without further ado, let's get into Kepler's laws. In June of 1600, Johann Kepler found employment as an assistant to Tycho Brahe, an astronomer living in Prague. Kepler began to study Tycho Brahe's precise astronomical observations. What Kepler found puzzled him. Why was Mars's orbit not circular? Copernicus's model of the solar system must not be complete. Mars's orbit was in fact an ellipse. This discovery is reflected in Kepler's first law. The orbit of every planet is an ellipse with the Sun at one of the two foci. This law focuses on the geometry of the orbit. The first question you may be wondering is, what is an ellipse? Isn't that just a fancy word for an oval? Well, no, they have a precise mathematical definition. Ellipses are most commonly described by polar coordinates, which are defined by a distance, the radius, as a function of theta, the angle. Usually, an ellipse's origin is at one of the two foci. The other focus is mirrored on the other side of the ellipse, and the distance between them is a function of the semi-major and semi-minor axes. Ellipses are easiest to understand through an example, so let's take a look at one. If we assume the Sun is the origin, and at the focus on the right, we can describe the radius of the orbit as a function of the angle theta, where p is the semi-latus rectum, half of the length of the chord that passes through the focus. And epsilon is the eccentricity of the ellipse, which describes how stretched the ellipse is. When the eccentricity is 0, the orbit is a circle, which is a special case of an ellipse. And if the eccentricity is between 0 and 1, the orbit is an ellipse. I'll make sure to cover what happens when the eccentricity is 1 or greater in another video. Let's start by taking a closer look at the parameters of a circular orbit. Because the eccentricity is 0, this term goes to 0, which means r is constant and equal to p. Pretty simple, right? Now, onto the more complex, but much more common elliptical orbit. In these orbits, the radius does change with the angle theta. The closest the orbiting body comes to the central body is called the periapsis, or r minimum, and by definition this occurs at theta equals 0. Its value can be found by dividing p by 1 plus epsilon. On the other hand, the furthest the orbiting body reaches from the central body is called the apoapsis, or r maximum, and this occurs at theta equals 180 degrees. Its value can be found by dividing p by 1 minus epsilon. When theta is 90 or 270 degrees, the radius is equal to p. The eccentricity of the orbit can also be calculated from these two values. With some algebra, we also find a mathematical definition of p. But don't worry about all of this terminology and math. You don't need to necessarily understand this to be able to understand the intuition. Okay, now that we understand the geometry, let's talk about movement. In 1609, along with his first law, Kepler published another. It states that a line joining a planet and the Sun sweeps out equal areas during equal time intervals. Funnily enough, He actually arrived at this law through incorrect and false assumptions. However, the law is logically equivalent to the conservation of angular momentum. If you're interested in the math, pause the video here, but I won't get into it. Maintaining angular momentum means the orbiting body trades velocity for radius, and vice versa. This law is what explains the orbital velocity changes for elliptical orbits. In order to sweep out the same area, the orbiting body must travel faster when near the central body and slower when further. It reaches its fastest at periapsis and slowest at apoapsis. Let's take a look at what this looks like in terms of elliptical parameters. Over a small time, dt, the orbiting body sweeps out a small triangle with base r and height r d theta. The formula for the area of a triangle is 1/2 base times height. So we get dA dt is equal to r squared over 2 d theta dt. By definition, the area enclosed by an ellipse is pi times a times b, and the time to complete the orbit is the period t. So dA dt is equal to pi times a times b over t, which is a constant. This law can also be thought of as the conservation of energy. In fact, using the principle of conservation of energy, we can derive the velocity of the orbiting body at any given point in the orbit. The total specific energy of an orbit is defined as negative mu, the gravitational parameter, over 2a. Specific here just means energy per kilogram, which helps keep the algebra a little cleaner. The specific energy is stored in two forms, kinetic and potential. The specific kinetic energy is the velocity squared over 2, and the specific potential energy is mu over the radius or distance from the central body. With some rearranging, we get the vis-viva equation, a common equation for calculating the velocity of an orbit. For a circular orbit, r is constant and also equal to a, so v is constant. Okay, now I'm sure you're wondering what the heck is mu? Well, it's a standard parameter of any celestial orbit that is the product of the gravitational constant and the sum of the mass of the central body and orbiting body. When the orbiting body is much smaller than the central body, this can be approximated as just the mass of the central body, which is common for spacecraft applications. At the time of Kepler's first two laws, however, this parameter was not known. It had to be discovered. And this brings us to the final law. With his first two laws, Johann had explained many celestial phenomena, but he was not done. He felt that there was more to uncover about our solar system, and he became obsessed with something referred to as the music of the spheres. There seemed to be a melodic, magical quality to the celestial bodies, and he intended to uncover it. He measured the mean distance and period of 6 planets and discovered what is now known as the harmonic law. About this discovery, he said, "I first believed I was dreaming." It states that the ratio of the square of an object's orbital period with the cube of the semi-major axis of its orbit is the same for all objects orbiting the same primary body. Kepler did not know it at the time, but this was a major step towards defining the gravitational constant that I mentioned a couple minutes ago, and was discovered by Isaac Newton. In fact, using Newton's law of gravity and centripetal force, we can derive this law for circular and elliptical orbits. If you're interested in the math, pause here. These Keplerian laws were a fundamental leap in our understanding of our place in the universe, and are a fantastic approximation for the orbits of planets and especially satellites, and are still used by aerospace engineers today. How do they make use of these? Well, during the early stages of space mission design, engineers need a basis to evaluate spacecraft and orbital designs. These laws provide engineers with a good starting point to try out new ideas. They usually do these calculations with software. I have access to MATLAB, so I'll show you how to do it there, but there are plenty of commercial and open source tools available that use similar formulations. Before I jump into MATLAB, I need to show you how we take Kepler's laws, which define a 2D orbital plane, into the 3D spacetime. We first need to define the geometry of the 2D Keplerian orbit, and we can do this with the eccentricity and the semi-major axis of the ellipse. I'll go with an eccentricity of 0.1 and a radius of 10,000 kilometers. Next, we need to define the orientation of the orbital plane in 3D. It must be defined with respect to a reference, which for planets is usually the equatorial plane, or the plane that intersects with the planet's equator. When the orbiting body crosses upwards through this plane, it does so at the ascending node. The right ascension of the ascending node or RAN, is an angle measured clockwise from the y-axis of the reference plane. This axis is defined by the vernal equinox, which marks the beginning of spring. I'll give it a value of 30 degrees. The vertical tilt of the orbit with respect to the reference is measured at the ascending node, and it is called the inclination. Since I want an orbit that goes over the poles of the planet, I'll give this a value of 90. Now that we have defined the orbital plane, we need to define the orientation of our ellipse within the plane. The argument of periapsis defines the location of the periapsis, the closest that the orbit reaches to the central body, and this is measured clockwise from the ascending node. I want my orbit to be closest at the south pole, so I'll give this a value of 270 degrees. Finally, we define the true anomaly, the position or angle of the orbiting body at a specific time, measured counterclockwise from the periapsis. This is where the orbit starts propagating. I'll start it at the equator, so I'll give it 90 degrees. And just like that, we can define an orbit and propagate it forward in time to simulate our spacecraft trajectory. If you've made it this far, thank you so much for watching. Please consider liking and subscribing so you don't miss future videos. Be on the lookout for my next video in this series covering how to escape and transfer between orbits. And if you're interested in the other side of aerospace engineering, I'll also be doing a similar series on aeronautics. See you next time.